My old grandmother always used to say, summer friends will melt away like summer snows, but winter friends are friends forever.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Oh yeah, baby, Franklin.
Oh my word! Guess who's back? It's Brittany, bitch. Is that what you should say? I don't know. It's what
Guess
the kids
who's
all
back?
say.
Franklin's back, but not only Jamie Franklin. We've got a podcast speed run going.
Oh my god! It's a big, strong crew here. Who have we got?
Got Julio. Julio, say hi.
Hi there.
Yes.
Chris,
Hi.
say
there.
hi. Hi there. we got the whole gang.
This
the whole
is a
gang
strong-
on a speed run.
This is a strong space podcast crew,
Right.
isn't it?
Yeah, it goes out on the 21st. We should mention that is the winter solstice, and also Jupiter and Saturn conjunction that you must go out and go and see.
Beautiful.
Once in a lifetime opportunity to see that. But yes, it's the winter solstice. Some people think it's the middle of winter. Some people think it's the start of winter, depending where you are in the world.
Now is the winter of our discount tents.
Hey,
there we go.
There he is.
And there's the first joke of the
There he is.
podcast.
That's why he's here. That's why he's here.
Right. As it's a speed run, we're going to go straight into space news.
Here we go.
Space news. Right.
Yeah.
Okay. So here we go. This is something that Julio's a bit of an expert on. And he'll cringe now. I can see it.
Now you put me on the spot.
No pressure.
So yes, lots of ESA news. My WhatsApp from Julio was going crazy because he keeps sending me all these ESA news.
It was a busy week.
Sabre-powered reusable launcher. ESA have been sort of looking into that and looking into the benefits that it might bring.
Yes, we did a system study. Reaction Engines has been working a lot on the Sabre engine for a long time. It used to be coupled with the Skylon spacecraft that you guys mentioned lots of times as well. They have been looking into other uses for the Sabre. So there was this study just to see how it worked with a 1 or 2 stage reusable configuration with a sort of space plane at the beginning, but that could have inside a first upper stage in a normal rocket, but it would come out of the bay, and then it would deploy the satellite. What is interesting is that from the ESA side, mostly we have always been working with them on the development of the engine, and this is first time that we really look into the whole system on my directorate in particular. We did a study as well, similar to this one a few years ago, comparing this on how it would work with Skylon as if it would work as an airplane, as an airline instead of a rocket model.
Point to point. It's kind of what Musk wants to do with Starship, but that seems less feasible without wings.
It has some tiny wings.
Tiny wings.
Little ones.
Yeah, I'd be a little bit stressed with those tiny wings. Jamie,
Hello.
can you remember podcast 100?
Oh, I do, because that surely was the one that we were at the BIS, wasn't it?
We're at the BIS, and one of the things that we announced on podcast 100 on our live show was astronaut Matthias Maurer being made an astronaut, an official ESA astronaut.
Yeah.
So that was at that time. So yeah, and now this is super exciting. He's been assigned his first flight, which is aboard a Dragon, which is Crew 3, which is actually pretty epic, I reckon. And get this, for extra epic, it looks like me and Julio might be chatting to him very, very soon.
I mean, that
Right,
is,
Julio?
That is big.
Does
Julio know about this?
Stressing the word might.
Might, yes.
It's
yes,
in the
absolutely.
plans. We'll see.
It's in the plans.
We love a challenge. Well, I'll tell you what, Matt. Can you tell me the name of the mission?
I can. It's the name of one of your favourite videos, Cosmic Kiss.
Oh, yes. I mean, it's been some time since I've seen it. But yeah, incredible. Oh, dear.
Chris, do you know anything about Cosmic Kiss?
I want to learn as much as I possibly can about Cosmic Kiss, please.
It sounds like the most insane tribute act of all time, doesn't it? Imagine get that.
It does.
Kind of like a space version of Kiss there. But yeah, I mean, impressive stuff.
Yeah.
But yeah, what a legend.
What is behind the name is a sort of love declaration for space.
We're all for it.
And but what I liked very much about this mission is the patch. Maybe you can add it into the show notes, because this patch takes inspiration from the Nebra sky disk, which is the oldest known realistic illustration of the night sky.
Oh.
But not only that, it also it's inspired by the plaques inside the Pioneer and Voyager golden records.
Is that
our
what,
solar
is
system.
that the gold colour in there?
Exactly.
That is cool.
Yeah.
Amazing.
I love reading the thoughts behind each patch. You sort of look at a patch, and I suppose you could dismiss it, but every single patch seems to have a lot of thought going into it.
There is a lot of work behind these things, a lot of symbolism, and the name as well. There tends to be lots of inputs, sometimes contests. If you look at this one, obviously Kiss. If you look at the patch, the ISS of Kiss is highlighted red.
Oh my God!
Oh God.
Oh, that is clever.
What?
Oh wow, I hadn't spotted. You know what? I was looking at why is the K gold, but what I should have been asking is why is the ISS red? Ah,
And there you go, another acronym.
I've got one for Cosmic Kiss. God gave rock and roll to you.
Oh my God.
Oh,
I mean,
there you go.
It's
That's
incredible.
That can be the next ESA cover version after they went Bohemian Rhapsody.
Oh, you watched
That's
that
it.
one?
Yeah, I watched it.
Loved
I watched it.
You know, I take it as a challenge. These are the guys from ESA operations in Germany, the ones that control spacecraft. And now I want to get my people from the rocket side to do a video, but I haven't figured out yet for what song.
Well, we just told you. God gave rock and roll to you, and you could call the band Cosmic Kiss. What are you thinking, Julio? We've told you the whole plan.
And me thinking on Don't Stop Me Now.
That's another one.
Yeah.
That's another one.
So that's Tim Peake's Spotify edition. There we go.
Hey, Matt, to go slightly off tangent, I was looking up at the moon last night.
Yeah.
And it might just be the best moon I've ever seen. Beautiful waxing crescent, totally clear night, cold. Got my space binoculars out. Did you see it?
Yes, I did actually. I did see the moon yesterday because I was looking out for Saturn and Jupiter because it's getting more and more beautiful. But yeah, it should be tonight and tomorrow. The moon, Saturn, and Jupiter will be epic.
I've seen a lot of great photographs already on the interwebs, but it's been very cloudy and rainy here in Norway. The country's given me a very wet send-off, but it's a shame. But certainly didn't see any aurora borealis, I can tell you that much.
You know, I saw a photo of Saturn and Jupiter with its 4 moons, or 4 moons visible anyway, and it was taken on an iPhone that was pushed up against a telescope. I mean, but it was so incredible. I just thought, my God, in 20 years' time, how good are the photos going to be?
It's I interviewed a couple of space astronomers and astrophotographers this week, and yeah, their pictures are incredible. They combine painting and astro, so that's one coming out soon. So yeah, astrophotography is just getting insane now.
Nuts, isn't it?
Well,
you don't really need to spend thousands to get a good image.
Yeah, I was just thinking of Cosmic Kiss after we've realised what an ace name that is, right? Who can tell me out of you three what the name of the Space Force, what they're going to call the Space Force people?
I got it. Guardians of the Galaxy.
No.
Amazing. No,
Are they actually?
They're going to call them Guardians. This is after a year of. This is several years of consultation and experts and space experts, and they came up with Guardians. I'll leave that up to you to decide. We are the Guardians. So yeah, that's quite cool. Let's do a couple more ESA things because we're never going to do this speed run. If ESA plans a demonstration of reusable rockets.
Yes, have you guys heard of Themis?
We've mentioned Themis, I think, twice on the podcast. It's a name that I should imagine is going to start getting used more often, or usually in relation to Prometheus as well at the same time.
In the relation to Prometheus, very good. Yes, we have been doing several activities connected to reusability in one way or another. You guys have heard of Space Rider. We did it. We mentioned it last week. You had an interview with Giorgio Tumino. We have done other activities, mostly within FLPP, Future Launchers Preparatory Program. Yeah, some of them were like hopper tests, which were done in Romania. There is a project called Callisto, in which you have the JAXA, the Japanese, Germany, and France working together on that. And now this is like the big brother, Themis. Ariane Group and the French space agency CNES have been working on this already for 1 year together, approved and added to the ESA portfolio in the last ministerial conference about a year ago. This last week, we finally signed the contract, and this means that now it becomes part of the ESA portfolio of projects. It's a first stage demonstration. Stress on demonstration. This is not how we're going to finally use it on either a future version of Ariane 6 or Ariane 7 or whatever we call it, but it's a demonstration of the technology. And then we build knowledge here in Europe, we develop industry, and then we see as well if this makes sense for us or not.
Ooh, so it's a long journey, isn't it? So
yes, we are looking into the 2030 more or less to use it.
Will we see videos of landings by European spacecraft anytime soon?
I certainly hope so. If I remember correctly from what we wrote, 2023, 2024, there should be some hop tests in Sweden. I published a very nice. I'm saying that my own diagram is very nice.
Good man.
It's beautiful.
If you say so yourself.
I didn't do it. I got it from the project, and I really liked it. I think they did a very nice job. It was prepared by an organization called Ariane Works, because we like to mix all these organizations together. Ariane Works is like a joint venture between Ariane Group and the French space agency CNES. According to this, we'll do some hop tests in the year 2022 in Kiruna in Sweden. And after that, we will move to Kourou in French Guiana. I think you might have been there, Matt.
Oh, yeah.
We'll do longer flights, more tests. 2025, we will do a full test. What we're trying to do here is trying to developing different building blocks. In a few years, we need to decide what we do after Ariane 6 or what we do after Vega C. We have already developed some of these building blocks, and we can put together the next rocket like a Lego. You have your parts already developed or pre-made, or the technology pre-made, and then you can mix them together much faster than if you have to start everything from scratch.
That's actually really exciting. It's almost like all rockets are going to start to be flown and landed soon.
Yeah, but as you see, it's not the only thing we are testing. We are also looking into Saber, as we discussed earlier today. Yep. Space Rider. There are many different approaches to reusability, and we are looking at some of them.
What about space elevators?
You had a podcast on space elevators.
Yeah, that's what
I
I'm
actually
asking.
translated a book on space elevators like 10 years ago. That was like my first paycheck related to space. I love the concept of space elevators. Definitely not updated on the latest to know if it's feasible from the materials point of view or not. And then from the design, as usual, the devil is in the details, okay? The concept of how a rocket works is very simple. But then to make a rocket work can get very, very complicated. There are many things to take into account. So I think we are now at that stage on the space elevator in which, yes, you can define the system, but the day that you have to start building it, you are going to run into so many unexpected things, as with any big project. I'm sure the Egyptians had this trouble when building the pyramids. They said, well, let's build this simple triangle, and then probably when they started building it, they realized it was a little bit more complicated.
Yeah, but they did.
They had a large amount of slaves on hand, though. That was the main advantage that they had.
Did.
Yeah. Unfortunately, the slave sort of plays into the first rockets as well. But let's not go into that. Happy Christmas, everyone.
Yeah, it's all very difficult.
God bless us, everyone.
Last bit of ESA news. We've got a new Director General, Dr. Joseph Ashbacker. I'm assuming that's he's German, is that right?
No, he's Austrian.
Austrian. I'm very sorry.
Classic mistake, Russell.
That is a classic mistake.
German. Jan Werner, our current Director General, is German.
Right. Okay. But this guy, I believe, he's kind of made his way up through the ranks. He's been staff as Director of Earth Observation, and he's made his way all the way through. And now by the 30th of June, he's going to be.
Yes, in fact, I was just reading now that he started at ESA as a young graduate trainee. So in your early 20s, right after school, you can join ESA in one of these 2-year programs. And this is like how many people working at ESA have started. So this is a guy who has made it through the ranks. I interacted with him only briefly, always a very, very pleasant guy. I look forward to see what he does. He has been a huge success with dealing with ESA, dealing with the Copernicus program.
Yeah, well, Copernicus is amazing, isn't it? So if he does, if he makes ESA as good as Copernicus, then boom, we're done now.
What excites me as well is that he always put a lot of emphasis in the importance of communications. On telling the public, on communicating with the public, and well, as you know, I liked working in that area, so I look forward to see how he brings this to the big ESA picture.
Right, so the Space Awards 2020.
Whoa! Oh, yes!
Here we go.
Here we go.
Oh,
there you go.
I'm actually quite surprised by some of these results. I'm actually quite surprised by, but they were pretty unanimous. These, as in whoever won each category did it by quite a margin.
There'll be those 1,000 votes I put in for each.
Yeah, I did actually discount your vote, Chris. I did notice it. I did notice it come in, but I discounted it because I thought because then I'd start voting, Jamie would start voting. I did put Brian Cox's vote towards it, but it didn't make any difference. It didn't even his vote didn't even get in the top 3. So Jamie, as promised to the readers, you're going to read out the Space Awards. But before
it'd be an honour.
Before we start, Jamie, tell us a little bit about your life in between episode 200 and 216, because there's quite a lot to tell, isn't there?
There is a lot to tell. Yeah, it's pretty crazy. I don't even know where to start, really, but it's been fun. I've been learning how to record music into my computer, Matt. All the kids are doing it. I've written 4 or 5 very average songs without words yet. Mm-hmm. But as soon as they're done, I'll send them across to you. But of course, there has to be a 7th now that I've heard of Cosmic Kiss.
Oh, yes.
You know? That's got to be the name of my solo project, surely. But yeah, it's been fun. I've missed all you guys, and it's nice to kind of come back. And I tell you what, Matt, what an episode to come back on, eh?
The Space Awards.
We got quite the guest.
Oh my God,
so
yes.
Excited.
And the guest is insane. The guest is massive.
If you'd have told me that when I was about 11, if you'd have told me that I would be introduced to my space hero by Nick Rhodes from Duran Duran, I'd have said you were absolutely mental.
Is that how we met?
See what he's done there. So yeah, that's how it happened. So yeah, old Coxie, he's been on our number 1 list, hasn't he, Matt? For over 4 years. Mm-hmm. We eventually got him via the help of an 80s synth legend.
Yeah, that's quite.
So there we go. It came full circle.
Nick Rhodes clang. Okay, then. So Jamie, we've got 4 categories.
We have.
Yeah. So, do you want to read out the best space event in reverse order from 3rd position onwards?
Here we go. Best space event. Number 3, we have Starship Hop.
I can't believe that didn't win. I just can't believe it. It didn't even come close to winning either.
I mean, blimey. Here we go. In 2nd place, we have Chang'e 5's landing on the moon.
Yeah, and we do have to mention that Chang'e 5 brought back lunar samples. So that whole mission was a complete success. They've actually brought back moon rock. That's just insane.
I mean, yeah, it is ridiculous.
One of the headlines I saw was moon rock found inside capsule of Chinese. Yeah. It was just like, oh, come on. Yeah, that's what they were expecting to find.
Yeah.
Yeah, that's always a little bit disappointing. So who won, Jamie? What won?
Okay, ready? And first place, Matt, was Crew Demo 2 and Crew 1. Yay!
Yeah, absolutely smashed it. Literally 90% of the votes were for that. So obviously that's the thing that...
Yeah.
So better than the belly flop, better than moon sample return was the return of American spaceflight and commercial spaceflight at that to the ISS.
So exciting.
So, best space legend.
Coming in joint second is Christina Koch and Victor Glover.
I must admit, that surprised me.
I was rooting for Victor.
Which means it's everyone charge their drinks.
Everyone
it's
get ready.
At first place, Mr. Elon Musk.
Drink!
Here we go.
My wife's just bringing me a beer now.
There we go. Perfect.
Now, this one did surprise me. Not. So, here we go. Best rocket, Jamie. Your favourite category.
Here we go. Third place, we've got the Electron. Second place, the Long March 5. And of course, in first place,
again,
Falcon 9.
Falcon 9, yes. I got it. Yeah.
It's killing it.
There we go.
Absolutely killing it.
Yeah.
Matt, what about best bit of space science?
Well, best bit of space science in third place. In third place was finding an FRB in our own galaxy.
Yeah, it's not bad, is it?
That was pretty. Yeah, so that was a couple of weeks ago. But it's a joint winner. Literally, no, it was. They had equal votes.
Did we just go from third to first?
So we've gone from third to first. Yeah, because
okay. Well, I mean, I'm all for it.
Well, there's a joint winner. So you're third, aren't you? If there's a joint winner.
Well, we're going to have to pick our favourite one.
Oh, so it goes down to the judges.
It's got to be. So we've got a choice of Hayabusa sample return and phosphine in Venus's clouds.
Oh,
what are we saying?
Julio. What you saying? Phosphine? Chris?
Julio's going phosphine. Chris?
Phosphine.
Phosphine as well.
If we can, this will define future missions. And imagine if we find life in Venus, it just changes everything.
Yeah,
everything.
True.
So there we go. It's a double one. Matt, what do you reckon?
Well, I'm going to go with Hayabusa sample return because phosphine is not looking. It's not necessarily right. There's a little bit of a question mark.
We had that confirmed by Professor Brian Cox.
Yeah,
didn't we?
So Brian was not a massive fan of the phosphine one.
Can I change my vote?
So Jamie, you have you actually have right.
I've got the casting.
You got the casting vote. You could throw it back into a draw.
Oh my god! Well, only because Professor Brian Cox was on the fence about it. I'm going to go with Hayabusa.
Yeah.
Oh, wow.
Yeah, Hayabusa.
That's how we roll.
Yeah, Hayabusa. Well done, JAXA, because I think that is one of the best missions.
Incredible stuff.
Ever.
Well, thanks to everyone that voted, eh?
Oh my God! Not only that, everyone had a little chance to write something at the end, and there were some really, really nice comments. And so I thought I'd read out Todd Barnell's, and he said, "Thanks so much for all you do, all the energy you put into this show, and all the hope and awe you help us feel. I'm awfully proud to be a Patreon, so I can be a tiny part of the awesomeness." So I thought I'd read that out to you guys as part of the...
That is incredible.
It's part of the Interplanetary podcast and what it means to other people listening out there in the wide world.
I think it's good. I think it's a bit dusty in this room.
You got something in your eye, Chris?
Yeah, I think so.
That's
lovely. That's lovely.
Do you know what?
There we go.
I had loads lined up for this episode, but I think the Brian Cox interview is so long. We're going to have to pass over the fact that the Big Bang has been confirmed by some Australians out in the outback, and we're going to have to pass over the fact that there's been a tantalising radio signal from Proxima Centauri as well.
Whoa.
I know.
Cue the tabloids.
Another wow signal. Highly unlikely to be aliens, as Lewis Dartnell pointed out in The Guardian, which I thought was quite funny.
And we will briefly touch on the fact that China managed to get lunar samples back on Earth. That's huge.
Oh, yes, very true, because that is insane.
I do think that the Chang'e 5 mission is one of the best things that's happened this year.
It's huge. It's huge.
It is absolutely huge. Yeah.
No, you have only the Americans and the Russians that have done this in the past.
Yeah, but there's some extra bits, isn't there? The fact that they were able to rendezvous, they were able to land on the moon, take back off, rendezvous in orbit, and come back, means that the Chinese have got all the technology and all the know-how to be able to do manned missions to the moon. It's huge. Not just the sample return, but everything else. It's epic.
Superb.
I used to have a teacher called Rendezvous. Weird, isn't it? Yeah. I think he was French.
Oh,
did you have little
rendezvous?
Did you have little secret trysts with them behind the bike sheds?
You can't speak about that. I'll get in trouble. All right, so where are we at, Matt? Let's wrap this up. Should we introduce the guest?
Yeah, let's do it. For us Brits, I mean, I guess he must be the most famous science communicator in the world. Maybe Neil deGrasse Tyson is the one up against him, isn't he? Really? Mm-hmm. So, but
it could be.
He's what a lovely. I have to say, Jamie, I could not believe. I was blown over by how knowledgeable he was. I mean, he could talk about any subject that we threw at him in great detail. I mean, he is proper on it. He's
including, as we'll find out, synthesizers,
even synthesizers, and taking them apart.
Yeah.
And also, he was just a lovely bloke who absolutely loved it. He loved talking about science. So that was.
He really seemed to enjoy it, and just a joy to have him come on, be really generous with his time. Because a lot of people like that sometimes give you 20 minutes max, but an hour and 15. And it was an absolute joy. So we were punching the air, weren't we, Matt, at the end?
I mean,
so we hope you enjoy it as much as we did.
Yeah, if anything, we finished it, didn't we? I reckon we could have had him on all day. he just loves talking about science. So, a Kute.
Roll it.
The Interplanetary Podcast, putting the ace back into space.
We are joined by the one and only Professor Brian Cox. Brian, thank you for joining us.
Absolute pleasure.
This is really exciting. I think one place I wanted to start was when I knew that you'd accepted the interview, I went into a deep dive on YouTube, which is good and bad. But one of the good things is I got to hear a lot about, I know that Matt, who is obviously our co-host here, and your heroes is Richard Feynman. And I went to read because I hadn't read The Value of Science, and I know that it crops up a few times in some of your lectures, and it blew me away. And I can see why you're so enamored with it. And that some of the quotes in there, and actually one that really stuck out with me was him when he said he's standing at the shoreline alone, and he's looking out at the sea, and he describes the sea being tortured by energy. Thinking of the billions of years that have gone past with no one to entertain. I just thought, what a quote. And as you mentioned a couple of times, the satisfactory philosophy of ignorance, just incredible way to sort of shine a light on the doubt being okay.
Yeah, it's really important. I mean, he wrote that, the context is, it was a speech he gave in 1955, and it was off the back of the Manhattan Project. And actually, Oppenheimer, who ran the Manhattan Project, was doing similar things. There's a BBC Reith lecture from 1953 where Oppenheimer says similar things, that they both were surprised they were still alive because they delivered this power to politicians, and they were both deeply suspicious of authority and politicians, actually. Not surprisingly, if you'd grown up through those times. And so they were reflecting on the value of civilization as well. And as Feynman says at the end, what's the most important thing that science teaches you? It is humility. And that's surprising to some people, because I think there's a view of scientists that we're kind of, there's some arrogance, you pass these truths down from this mountain and you go, well, if you don't believe that the earth is a sphere, then you're an idiot. You probably are in that case, probably a bad example. But anyway, but you know what I mean? It's kind of this, when actually, as Feynman points out, science is about doubt, in the sense that you have to recognize what you don't know in order to make progress. Because if you think you know everything, then you don't do any research. You don't do anything. And that doesn't just apply to science. It applies to politics, as Feynman says. I mean, I love the bit in that essay where he says that democracy is a satisfactory philosophy of ignorance. Because in order to be democratic, you have to understand that you change your mind. Power shifts from one group to the next. That's an admission that you don't know how to run a society. And that's not a negative thing. It's an extremely positive thing. Obviously, in democracy, the most important bit of democracy is the peaceful transfer of power. The fact that sometimes the power goes to people you don't like and sometimes it goes to people you do like is kind of secondary. The point is that we recognize the fact we don't know how to do it. And that's what I think is a very deep realization. And Oppenheimer says the same thing. And it's interesting that we find ourselves in a time perhaps where we have to remember that. You know, there's a lot of certainty in politics at the moment. So, you know, in the US and elsewhere, there are a lot of people who are in politics who think they're right. And actually, the fundamental point that Feynman's essay is nature hammers it into your head, especially when you're a research scientist and a postdoc and doing your PhD and so on. It hammers it into your head that you're usually wrong. Right? Almost always. Every scientist I know is wrong doing research, you know, probably 99% of the time. But the point is that science is a mechanism to allow you to get to the 1% bit where you're not wrong. You're not absolutely right. Never absolutely right. But at least you're not wrong.
What's remarkable about Feynman is that he's so down to earth about it, isn't he, as well? His two biographies, the Surely You're Joking and the other one, I keep rereading them because I just think they're just unbelievably fantastic books, you know, just as almost like as a philosophy of a way of living, more than just the science in them as well, because I think he really sort of understands that. But while we're on the philosophy of science, I've got a question that I didn't actually mean to drop in so early, because it's kind of deep, and obviously as a sort of podcast host, I realise I'm probably batting way above my weight here. It's a classic example of the Dunning-Kruger. But the last sort of 25 years of, say, particle physics, I think have been really disappointing. If you compare it to, say, astrophysics or something like that, where we're clearly in a golden age of discovery after discovery after discovery. And particle physics with the Large Hadron Collider, you got the Higgs boson, but it's been a bit of a disappointment from there. So some people call it the nightmare scenario. But is that down to a philosophical mistake that people are coming up with lots and lots of different hypotheses for what, say, something like dark matter is, or all these other, and just assuming that the standard model of particle physics doesn't look good, it doesn't feel like it's really awkward, and therefore there must be something more to it that we're missing, and this drives them to put their hand out and say, we need to build a bigger, larger Hadron Collider. I know there's a load to unpack there, but what are your thoughts on all that element of it all?
Well, the kind of first thing, the preamble to your question is, of course, as many people have said, nature really doesn't care what our expectations are. What we're doing is exploring nature. So we discover nature as it is. And if it's not, it's usually much more interesting than we can possibly imagine. If it turns out to be less interesting, then that's just tough, because that's what nature is. But you're right, in particle physics, we build big machines. So there's a business element to this, right? You've got, if you're going to build a Large Hadron Collider, the most complex machine ever built by some measure, then you have to have a case for building it. And it was very clear with the LHC. And the case was that if you look at the standard model, which as you describe is our model of all the interactions, the three forces of nature other than gravity that we know about, fundamental forces, so the weak nuclear force, strong force, and electromagnetism. It's a model that works, but it does not work at LHC energies without a Higgs or something else that does the job of the Higgs. So what we had was a very clear, the jargon is energy scale, but we knew that if we hit protons together at these energies, we would either discover the Higgs or a variant of a Higgs or something else that does the job. So you know you're going to add to human knowledge by building that machine. And so that's why it was built. And indeed it did. Right. So what we discovered was that as far as we can tell, the simplest model, which is the standard model Higgs particle, it's called, appears to be the way that nature operates. It didn't have to be the case. And actually my most cited paper, which has got, it's really a very successful paper now, actually. I think it's 600-700 sites. I can't remember what it is, but it is basically about physics at the LHC without a Higgs particle. Right. And it's a successful paper because it was written back in 2001, I think, something like that. So we didn't know, but it developed some experimental techniques that are widely used now. So that's why it's successful. But it was a very real possibility that we would discover something else. Just a very simple, you might say, how do you know, by the way, that a theory breaks down? Basically, it was predicting probabilities greater than 1 that things would happen. So the Higgs, the fancy word is it unitarizes the WW scattering cross section for people that want to know. But it basically meant that if all else failed, if you bang these particles called W particles together and you can't make a Higgs particle, you've got to make something in there, something new. But basically was the point. But you're right. So now we have a model with the standard model Higgs, and it doesn't tell you where new physics appears, right? We're very sure that it is not. I mean, it is not a complete model of the universe at some fundamental level. So there is something else, but there is new physics, but we don't have a very clear indication of where that is. So that means that you don't know how big or powerful the next machine has to be to guarantee that you'll discover something else. So that's probably, you're right, a position that we haven't been in particle physics for a long time. It's not to say that we won't get a signpost from LHC. So LHC has not taken, it's taken just a few % of its design data. And really, so now we move into we're still searching for new physics. New particles that we've not yet seen, because it might be that they're made. It's very unlikely you'll make them, so you have to get a lot of data to find them, to find a clear signal. So we're still doing that. But it also, the other way you can do particle physics is to make precision measurements, very high precision measurements of, in this case, for example, the way the Higgs particle behaves, and that's what we're doing. And in those precision measurements, it has happened in the history of particle physics that you see something that is anomalous, that stops behaving as you think it should, and that's the sign of new physics. And that can tell you, that can be a signpost to where you need to go next. But as you say, in the absence of that, what you can do is say, okay, we're going to explore the Higgs particle then, for example, very carefully. So we'll build a machine that makes Higgs particles very cleanly. That would be a linear collider that people talk about, where you bang electrons together instead of protons. And I should say, for those listeners who aren't familiar with all this jargon, protons are enormous things full of stuff, right? They're messy, huge things in terms of particle physics. So when you smash them together, yes, you get some nice clean production of something like a Higgs particle sometimes, but also you get debris scattered over the place. And it's a complete mess. And a lot of the work in particle physics is getting rid of all the mess, the noise, so that you can see the bit that you're interested in. With electron colliders, electrons, as far as we know, as far as we can tell, have no substructure at all. They're just things that beautifully, cleanly bang together and cleanly make whatever it is that you might make. So the standard kind of idea in particle physics is electron colliders are easier to do precision physics, and proton colliders are easier because you can get higher energies to discover stuff. Not quite true. And if some LHC people are listening, they get very upset because it is true now that we are so good experimentally that we can do real precision measurements with proton colliders, but they're quite messy. I think no one would disagree with that.
Yeah, I mean, do you think that some particle physicists oversell Because I mean, just listening to you then, it seemed to me, and obviously you can correct me, is that without the new signposts, really asking for the bigger machine seems to be a tall order, because you're saying, yeah, we're not quite sure where we're supposed to be going with this, but let's just build something bigger. Now, and I've got, obviously, I love it when science asks for money, because after all, it's their money at the end of the day. It's generated by, all the wealth has been generated by it. But it's like, but is there better projects that money could go on?
Well, it's always the, it's very complicated when you assess big international projects. You're right. And so there's a very good science case you can make, because we know what measurements, in the absence of any signposts, we know what measurements we should be focusing on to make the useful precision measurements that will, you would guess, will open the road to new physics, right? So you can make very nice arguments about big machines. But you're right. So you're asking a question really about how do you make decisions internationally about which projects to build, and there are clear science cases. For example, as you said, we'll talk about it. Gravitational wave physics is tremendously exciting and productive at the moment, and I think the case for a big gravitational wave detector in space is, to me, overwhelming. Also, looking at the cosmic microwave background, which we'll probably talk about as well, these collecting the oldest light in the universe from close to the Big Bang. Very strong case for making high precision measurements of that. So, but there's also a case for going at the other end of the scale, which has been tremendously productive for the last 50 years or more, of exploring the Higgs particle. Now, the Higgs particle is a completely new sort of particle. It's what we call a fundamental scalar in nature, and it brings with it a whole load of baggage that is very difficult to understand. The standard model itself is ultra fine-tuned, we call it. So it's all very delicately balanced, and this leads into issues about the stability of the universe as a whole. Actually, I'm not scaring people here. It's not the universe is going to fall to bits.
Yeah.
But over long time scales, there's this thing we call are we in a false vacuum state? All these things. So there's a load of fundamental physics there. One of the things you have to think about when you think about new colliders, and we've seen it actually, is that particle physics, building particle accelerators, is as much of an art as a science. And you see this when I was very heavily involved in a project called FP420 a long time ago at the LHC, where we were trying to modify part of the LHC to put detectors very close to the particle beams, which is still a very nice project actually, and we've done it partially at LHC, but we haven't done the full thing that we'd hoped to do. But that meant I got very involved with accelerator physicists, and you find that I bet you we should talk about it. It's like building synthesizers, I reckon, in that there's a huge amount of experience involved. It's also like building a Saturn V rocket, by the way. You wanted to build one of those, you'd struggle now. We have different ways of doing it, but there's a continuity of expertise that if you lose it, it is extremely difficult to get it back. And so I think that there are strong cases scientifically to be made for new particle accelerators. But there's also other considerations. There's a very strong idea that we do need to be able to build particle accelerators. I mean, they're widely used in medical physics, for example. And so I think it's difficult how you choose these next big projects. I think CERN, by the way, is the way to do this, because it's a lot of countries contributing a little, and it looks expensive because it's a big machine. By some measure, it's expensive, but its budget is actually less than the University of Manchester's budget, right? Yeah, so it's less than the budget of a medium-sized European university, but because everybody pays in and it's focused on one thing, which is the exploration of nature at the smallest distance scales and the highest energies, you can do it collaboratively without really impacting too much on national science budgets. And also, I should say, of course, that CERN, it almost doesn't need to justify itself in a sense. If you say, what's it done for us? What have the Romans done for us? You can stop at the World Wide Web.
Yeah,
right. I mean, it's done a lot more than that. It's done a ton more than that. But the conversation is gone. There's a great document in the archive at CERN, by the way, which Tim Berners-Lee uses in his talks, which is it's a piece of paper. I think it's 1989 or something. I can't remember. It's 87, 89. And it says the World Wide Web and Information Management Proposal, right? So it's his thing that he wrote to his manager. Said, I've got an idea, right? I've got this thing, the World Wide Web. And his manager wrote vague but exciting on it. And it's in the archive. It's in pen, in biro.
Wow.
Vague but
exciting. God.
The key point is though, carry on.
Class. Wow,
Yeah, carry on.
incredible.
Carry on. I don't really get it. He's basically saying, I don't really get this, but why not?
Yeah.
We're a research lab. Have a go.
Well,
See what happens.
Which is exactly what I meant by the sort of that science should never sort of feel like it needs to have the begging bowl, because it's like well, all this money, by the way, that we're asking for, we kind of generated.
Yeah, and someone tweeted. So what day is it today? 16th of December. We're recording this. I saw a tweet this morning from an American epidemiologist. No, he's a vaccine expert, professor, expert in vaccines. I don't know him. It just came up on Twitter. But he just said that all those people who are calling this vaccine a miracle are wrong. Right? It's built on decades of fundamental curiosity-led research. That is why in 12 months, from a new disease appearing in humans to a vaccine, that's why it happened in 12 months. It wasn't a miracle. It wasn't something that came out of the blue. We're not lucky. Right, it came from decades of investment in curiosity-led research. Tens of thousands of people who've gone through the education system. It's the ultimate, Newton's quote, standing on the shoulders of giants. There can be no better example of that quote than this vaccine development. And it's some of the technologies that were used are technologies that nobody, no matter how smart, would have thought would lead to vaccine development, right? Because they're fundamental knowledge, things that were invested in because people were interested and curious. No obvious link to the real world at all. But all that stuff feeds into something that turns out to be useful. Same with CERN. The spin-off technologies no one could have predicted. So the World Wide Web being one. The use of accelerators in medical physics, now cancer treatment, hadron beam therapy or proton beam therapy, which some people may have had direct experience of. In fact, life-saving treatments. They use particle accelerators. We didn't start building particle accelerators to do medicine. We started them because we were interested in the structure of atoms and the structure of the nucleus and so on. I mean, Rutherford in Manchester, right? So essentially, he didn't have a particle accelerator, but he kind of used a natural one to bounce alpha particles off some gold foil to discover the nucleus, right? Yeah. And from then on, you say, well, can I build some technology to get faster alpha particles or faster probes of matter? And suddenly you work out how to build particle accelerators, and then you find out that they're really useful. If you fire proton beams towards tumours, they can destroy the tumour.
Yep.
So talking of CERN, Brian, what's the current biggest challenge at CERN?
Well, I think it's what we do always in particle physics is we want what matters is the energy of the collisions, which is pretty much set by the machine, right? So you can't really increase the energy, but you can increase the number of collisions per second, and that gives you, because particle physics is statistical. So it's 1 in 10 trillion or whatever it is. I can't remember the number of collisions. You get a Higgs particle. So the more collisions I can have, the more Higgs particles I make, and the easier it is to study them. So the more collisions per second, the easier it is to make precision measurements and make discoveries. Except that the more collisions you have per second, the more messy it is. And so the accelerator physicist will deliver you more collisions per second, and you get loads of particles colliding. So it's almost as if every photograph you take, you have not one proton collision, but like 30 collisions. So you get this, and there's only one of them that you're interested in. The rest is a mess. So then the experimenters have to get better at data analysis and upgrade the detectors, which are the cameras, in order to pick out the interesting stuff. There's more interesting stuff, but it's filled with more noise. And so it's an ongoing challenge, really. So those are the real world practical challenges. So we want to get more data and get better at looking at these very complicated photographs and seeing the thing we're interested in and measuring it more carefully. Ultimately, the hope is that we see a sign of something new. And we're nowhere near the level where we think we won't see anything new. We're nowhere near that with LHC at the moment.
Is the problem in particle physics in particular, is it a lack of theories or a lack of data at the moment?
It's not a lack of theories. There are loads of them. But it's a good question. I mean, I think actually it's better to just look at physics as a whole. Particle physics and cosmology now are very closely intertwined. And also there are other non-accelerator based measurements. There's a very interesting measurement at the moment at Fermilab in Chicago, which is the way that muons, which are heavy electrons, behave in magnetic fields. And there's some deviation from the prediction of the standard model in that data, which is absolutely fascinating. So it's really what all these measurements, so measurements of coming now from precision cosmology of the early universe, and particle physics and the non-accelerator based particle physics, particle astrophysics, which is looking at things called neutrinos that come from space, for example. All these things are ultimately intertwined together. And ultimately, we're probing nature in different ways, at different energy scales and so on. But ultimately, you're trying to break our picture of nature, which is at the moment pretty consistent, with some very obvious examples that are not consistent, right? There's some really obvious problems that we can talk about. So we know there's a lack of understanding. We have a relatively consistent picture with the experimental data we've got. So the answer to your question is what you do is we know where the things break down. We know where the gaps are in our knowledge, broadly speaking. But you're right that it's in science, it's very difficult, I think, if you look at the history of science, to work out whether advances were seeded first from theory or seeded first from experiment. You can think of some very clear examples, but I think most of the time it comes from the overall picture. Barring some ridiculous discovery that you weren't expecting.
This is it. Brian, you mentioned the early universe. How close do you think we are to being able to see ripples of radio waves from the Big Bang?
Well, so electromagnetic waves you don't see because essentially earlier than 380,000 years after the Big Bang, the universe was opaque to light. It was in what's called a plasma state. So it means that there are loads of charged particles in a soup, sort of like the inside of a star in some sense. And light doesn't travel through that; it's opaque. So you don't see the oldest light, and same for radio waves that you can see, is essentially a surface. If you look out into space, you can see light that's coming from a surface, which is the point at which the universe was cold enough for atoms to form and the universe to become transparent. And that's called the cosmic microwave background radiation. So that's the furthest back you can see in time using electromagnetic radiation, radio, light, whatever. You can see earlier in two ways. One is theoretically, because the picture, we have a photograph of the universe 13.8 billion years ago, 385,000 years after the Big Bang, which has structure in it. It's got patterns in it. And those patterns are well understood. In fact, they were predicted remarkably by a theory called inflation, which we can also talk about, and then discovered. So there's a window, you can see some structure. And so you can say, well, how did that structure evolve? How did it get there? Gravitational waves, on the other hand, you can see in principle from the Big Bang. It's a very violent event that happened a long way away in this picture. I mean, the Big Bang happened everywhere, right? So every point of space that exists now was at the Big Bang. But the gravitational waves that we're detecting from the Big Bang are those that have traveled across the universe for 13.8 billion years, right? So they're very faint. They're much fainter than the waves we see from black hole collisions, but they're there, right? So the way you see further back in time is to build gravitational wave detectors that are sufficiently sensitive. And that must be space-based, I think. So we're looking at the projects that are aiming to build essentially laser arrays in space.
That's LISA,
between
is that right?
satellites. Yeah. So that's one of the proposals to build a machine that's sensitive, not only enough to see many more black hole collisions. We should talk about it. Tremendously exciting. So that's an experimental probe of black holes for the first time. You could argue we see them in radio as well. But also to detect these gravitational waves from the Big Bang. That would be great, because that's an image, right? It's an image using gravity rather than light of the Big Bang. And we can do that, right, in principle.
Yeah, so the multi-messenger element of physics, of astrophysics in particular, and it's just been like incredible, and that's why I was describing it earlier as the sort of golden age. It's just mind blowing.
Yeah.
But it's also, I love the fact that things like neutron stars and black holes are that crossover point between particle physics and the massive cosmology as well. Yeah. So so surely, like when you're looking at things like that, how much conversation happens between particle physicists and your astrophysicists, like over coffee? We're talking about the centers of neutron stars, for example.
A huge amount is the answer. The best example I can think of, which is the thing that I'm most excited about at the moment, is in black holes. So black holes, since the 1970s, have been the point at which particle physicists and people who do quantum mechanics and people who do relativity have been arguing, right? Because there's it's a beautifully simple problem which Stephen Hawking first identified, actually, in the 1970s. Many people have identified it as the best question that's ever been asked in physics, one of the best anyway. And it's just very simple. It's what happens on the event horizon of a black hole. And in particular, Hawking's question was what happens to information that you throw in. So if you throw a book or a hard drive or whatever into a black hole, what happens to it? Now, you might say, well, it's locked away forever, so we don't care. What Stephen showed in the 70s was there's a process called Hawking radiation, which means that black holes evaporate. So over a long, long period of time, it's something like 10 to the 120 years, right? So one with 120 noughts after it, for a black hole the mass of a star, a few times the mass of the sun or something like that. So that now the universe is 10 to the 10 years old at the moment, 1 and 10 noughts. So 10 to the 120 is a big number.
Yep.
But the point is that in principle they evaporate, they come back into the universe. They don't last forever. So then you ask, well, so the information doesn't get locked away then, presumably. So what happens? And Hawking, for many years, thought that the information was destroyed. Why? Because he did a particle physics calculation. In particle physics, the problem, the strange behavior of black holes is nothing to do with the black hole, right? Really, it's nothing to do with the singularity and all this stuff. It's to do with the event horizon. And the event horizon is the boundary in space, which is you can think of as a one-way boundary, right? That if you go in, you can't get out, which is the typical, I think, what most people think of as a black hole. You'd have to travel faster than light. If you go into that region of space, you're always in that region of space. And in fact, what happens if you go into that region of space is you go to the end of time, right? The singularity is the end of time. So you are going, you are ending, right? According to general relativity, you go in, it's as inexorably as you go to tomorrow, you are going to the singularity. And there's a very famous, in one of the great textbooks by Jim Hartle, he says that the singularity is not a place in space, it's a moment in time. Right, so you go to the future, that's it, you're gone, right? That's it. That's what a general relativist would say a black hole is. In particle physics, the structure of empty space, the structure of the vacuum is tremendously important in the way that we do calculations. And what you find is that if you take neighbouring points in space, they're what's called entangled with each other. There's a very important structure there that underlies all of our calculations in quantum field theory. If you stick a boundary in it, then you mess those calculations up. And ultimately, this is the where Hawking radiation comes from. So you end up producing real particles that go off into space, take energy away from the black hole, and it evaporates. So it's a property of the horizon. And the particle physics, the naive particle physics mechanism for producing that radiation is that it's got nothing to do at all with the stuff that goes in. It's completely different from if you burn a book, right, to be very 2020, if you set a book on fire, what happens? Well, what happens is that if you could collect all the ashes and all the gas and everything and measure everything that came off the book, then in principle, you could reconstruct the book. Absolutely fundamental. It's determinism in physics, right? It's absolutely fundamental. You could, now, obviously in practice you can't, but in principle you could. A black hole, because of the way that it produces radiation, not naively in Hawking's original calculation, there's no connection at all between the radiation that comes off and the stuff that goes in. So it looks like the information has been destroyed. When the black hole's gone, you're left only with Hawking radiation and no black hole. It's gone. And the Hawking radiation carries no information about what went into the black hole at all. That was the situation for years, decades. And so there's a fundamental clash. The other problem, by the way, is that there's a thing called the Equivalence Principle, which in general relativity is the statement that if you're in free fall, there is no gravitational field experienced. You see it on the International Space Station. Like, why do people float? Why is if you get a pen or something and let go of it in space, on the space station, why does it stay there? Einstein's explanation is because there are no forces acting, nothing's happening. That's the basis of general relativity. The equivalence principle is the statement that if you're in free fall in a gravitational field, it's not there. Right, it's gone. So in general relativity, if you fall across the horizon of a black hole, you don't notice. With some caveats about that, for a sufficiently big one, just for the pedants that are listening. But basically, if you can ignore tidal forces, which you can in a big black hole. So the event horizon is not anything when you freely fall through it. But in quantum mechanics, it's a very important thing because it's a barrier. It's a thing that disrupts the vacuum of space. Basically, it disrupts things. So you've got these two visions, these two views, which are a clash of theoretical pictures, right? And that has led, I think this year has been momentous because to a large extent that problem has been not entirely solved, but pretty much we understand how to solve the problem now. And it's remarkable. It's a remarkable thing. So you might have heard, people listening might have heard of things called the holographic principle. And the idea that, which comes from something for the more technical minded, that's called the ADS-CFT correspondence, that someone called Juan Maldacena was very famous for. But anyway, it's basically the point that it was noticed that before it was applied to black holes, that if you look at our universe, which is a four-dimensional thing with gravity and quantum field theory, then the whole thing can be represented in one less dimension, like on the surface. So it's as though you've got a sphere, to go to something we can picture, like the Earth, right? And it's as though everything internal to the Earth, everything underneath the surface, all the way to the center, can be described perfectly by a theory that just lives on the surface. Right, so there's a one-to-one correspondence, and this is used just as a technical thing in particle physics. So people will do calculations on the boundary in one less dimension, and they can do it, and then they'll transform it into the full four-dimensional theory, and go and look at the LHC data, and you get some results that you couldn't have got otherwise. So it's a very weird thing that you've got this physics. You can have the theory expressed in two different ways. And you can transform between them. That in black hole language, that has been very useful because it seems to be now there's a strong suggestion that really, that in a sense, and I keep using the word in a sense because there's some technicalities, but roughly, you're imagining some boundary to the universe, a way, infinity somehow, but some surface. And that's all there is. And you've got quantum mechanics on that surface, no space. And actually, probably no time as well. So space-time isn't in that theory, just quantum mechanics and the way that things are entangled with each other. And that develops the space. So space-time emerges from this quantum theory on a boundary, right? Now that's weird, and that's where the holographic principle comes in. So you're saying in a very real sense that we're holograms, right? That we're not really seeing the true nature of reality. The true nature of reality is just quantum mechanics. Space and time aren't in that theory. They come out, they emerge from the theory. So it's almost like the interior of the universe is developed by the entanglement of quantum fields on the surface somehow. So the surface is somehow the real thing. But the most amazing thing of all is that people have now worked out how to decode the information. How is the information stored on the surface? And how does that relate to the interior? And remarkably, the information is stored redundantly on the surface, in the same way that we have to store information in quantum computers to correct for errors in the quantum computer. So it's very difficult to do error correction in quantum computing. And it seems that the same coding mechanism is employed by the universe.
What?
Right? There's a redundancy. There's a redundancy in the way the information is stored. It's quite remarkable. So this realization, this swapping between theories and pictures, has been a collaboration, which goes back to your initial question, between relativists, people who do general relativity, quantum field theorists, and quantum computing experts. And the three disciplines together have now pretty much solved the black hole information paradox. The solution, by the way, is yes, the information comes out.
Wow.
So that's the answer. It comes out in the Hawking radiation. But in order to come out, it requires a complete reimagining of our view of space and time. Is that one way to look at it? There's a thing called the ER equals EPR, which is another remarkable thing where it's not quite right to say, but again, roughly, you can almost picture wormholes connecting the interior of the black hole to the far distant reaches of the universe. And in some sense, the interior of the black hole is also the far distant reach of the universe. The reality of the wormholes, because we all picture wormholes like Deep Space Nine and stuff like that and Interstellar, whether they look like wormholes mathematically or they actually are, is an open question that people are not prepared to approach just yet. Certainly in the public papers, people don't think about it, because it's not clear. But it seems, just to finish broadly, what happened was Hawking, in his original calculation, missed a bit mathematically. And the bit he missed mathematically, which tells you how the information comes out, looks like the mathematics of wormholes. So it's different. There's no real. I'm writing a book on this at the moment, and I haven't quite. No one's really popularized this science. It's very hard and very new. So my language is caveated and careful, but ultimately, I hope we'll do it in our book. Right? I'm writing with my friend Jeff Forshaw. Someone needs to do it, but ultimately, the point is that we're getting an insight through looking at black holes and the problems that they pose into the deeper structure of space and time, and actually most likely how it emerges from a quantum theory that does not have space and time in it. Well, which is quite remarkable.
Yeah, I mean that seems to be that almost seems to be sort of monumental, because I started the year actually with a conversation with Jim Al-Khalili about this whole idea of quantum physics and general relativity just being completely incompatible. But that sounds like that there's some hope there.
Yeah, it's more than hope. I mean, I think it seems pretty clear.
Wow,
that's what's going on. I think that because there's a lot of this ADS CFT thing works, right? This framework. I mean, people use it routinely now, and the fact that it seems to have this very clear application, I suppose is the right word, in black hole physics, is fascinating. Which then goes to which we talked about before, one of the ways that you start to test this stuff is ultimately the only way, right? I suppose is to make observation. And so as we get better at observing black hole collisions, you start to hope that part of this discussion, you may have heard of this thing, a firewall, which was one of the previous ideas, which is that a black hole, the event horizon, is both, you can both cross through it and not. So when viewed from the outside, the idea would be that it's a seething hot boundary. And so if you watch someone falling from the outside, they get vaporized. And out come their ashes, right? And there's all the information. But the equivalence principle tells you that if you fall in, if you're the person that falls in, you shouldn't notice. So you go in. And there's always been this sense, it's called black hole complementarity, that actually both happen. So both things. The reason you allowed both to happen, by the way, is because no contradictions emerge from both being true. So because very subtle effects, actually, that took a long time to calculate, you might say, well, okay, so this was Leonard Susskind and other people, one's a great genius who drives a lot of this work, or did initially. And then, so he imagined, well, what happens if someone jumps in and someone collects the information from their ashes, right, when they got incinerated, and then jumps in to meet them and says, look, I've got, I saw you, here's a photograph of you. It turns out and it's not an obvious calculation, but it turns out that because of the way that the timescales work, by the time, and it just works, by the time you've collected enough information to work out what's happening, and then gone in to go and meet them and reveal the contradiction, they've gone to the end of time.
It's too late.
So you can't get in fast enough. And it's to do with the way information is encoded and re-radiated, basically, in the black hole. It's quite complicated. But there's a time scale associated with how long you have to wait to make sure that you've got the information in order to see the contradiction. And by the time you've got that and got in there, they've gone.
See, Matt, this reminds me of some of
it's
our.
Unbelievable.
This reminds me of some of our chats down at the pub, where we often talk about what happens when you fall into a black hole. And Matt keeps telling me that I'm going to fall into the black hole, and then I'm going to be able to see the back of my own head. And whether that's true or not is almost irrelevant to the amount of sleep that I get that night. Yeah.
There's some of that. I mean, it's kind of interesting. The problem. It's easy to see what the problem is, actually, with black holes, because when viewed from the outside, and we'll teach this in an undergraduate course, right? There's a thing, again, for the experts called the Schwarzschild metric, and it looks like, so if you throw a clock into a black hole and watch it, then from your viewpoint outside, the clock ticks slower and slower. And what it does on the event horizon is it freezes. So from the outside, time is changing quite dramatically as you get to the event horizon, and it eventually stops on the horizon. You see that that's not a real problem. You can change things around, and if you jump into the black hole, you see that time passes at the usual rate for yourself, which it always does, 1 second per second, and so on. And that's just standard general relativity. But a lot of the problem comes in quantum theory from that timescale problem. When you adjust timescales, that you start to get interesting things happening in the calculations, and when you make time stop from the point of view of someone outside, then it gets complex, right? It gets difficult to understand. So that's why the fundamental reason why quantum field theory has a problem. But what's remarkable, though, I should say, the experts listening, they would jump in at this point. The point is that what seems to have been found is these problems, all this weird stuff that I just talked about, has not required new physics. It's required new mathematics and new understanding, but it's not required what we might call Planck scale physics. So we used to say, well, these problems will be resolved when we have a quantum theory of gravity. It doesn't seem to have required that. it's pointing, as you said, it's pointing towards a deeper understanding of space and time, which is presumably a quantum theory of gravity. But it didn't need that. It didn't need us to go, oh, there's some energies happening and things that we don't really understand. It doesn't seem to have required that. It seemed to require some quantum computing guys, ultimately.
Yeah. Oh, that's insane.
Go, no, it's this.
And Brian,
we know about that.
You mentioned worlds colliding. One of the things I was thinking about is I saw you talking about the multiverse, and I wondered whether there's anything that we could understand about overlapping Big Bangs. Obviously, we can only see out to a certain point of our observable universe, but is it possible that two universes could overlap? And if so, would we ever know it?
Yeah, so the thing you're talking about is the so-called inflationary multiverse, where there's so we're pretty sure. Some people don't think so, but most physicists, I think that before the hot Big Bang, so before the universe was hot and dense, the space-time was still there, and it was stretching very fast, which is the time we call inflation. And then the inflationary expansion stopped, slowed down, and the energy that was driving it got sort of dumped into space and heated it up and made particles, and that's what we call the Big Bang. And then the natural question to ask is, why did that inflating period stop at the same time everywhere? Why did it all stop at once? Could it not be there's a little patch here that stopped inflating and the rest of it carries on, and then another patch stops and the rest of it carries on? And so you're talking about, in some sense, multiple Big Bangs there, like multiple bubble universes being made all the time. And so I suppose your question is, can they be so close that they interact? Yeah. People have thought about that. Where would you see it? You'd see it in the cosmic microwave background. So you would see if you imagine, in some sense, these two things just very early in their development interacting, you'd see some asymmetry, right? You'd see some direction in space where there was some difference. And the cosmic microwave background, this afterglow of the Big Bang, is very uniform indeed, with little ripples in it that we understand that are predicted from inflation. But if there was regions where there was a real difference in this picture, you could say in the density of matter there, or the temperature of the cosmic microwave background, or whatever it is, then people speculate that could be a signal that there was once a very slight interaction with another of these bubbles. There is a region in the CMB which is in one part of the sky which is statistically a little bit different from the rest, and so, but not so much. And people have speculated that that's one of the explanations for it. It's not known. It's not widely accepted that. I think it's just one of those things that it could just be statistics. It could be something interesting. But yes. So in principle, the answer is yes. In
principle, yeah. Because I was thinking,
it is possible.
Two repelling gravities meeting. What would happen?
It'd just change ultimately the experimental observation would change the distribution of particles in that region. Somehow there'd be some signature, because if you think, if it made space expand a bit faster in that region, then the particles would be less densely scattered. If it made it go a bit slower, it'd be a bit more dense. And that's actually the explanation for the ripples in the CMB, by the way. The idea is that inflation, because of quantum mechanical fluctuations in the field that's driving inflation, called the inflaton field, inflation stops very slightly differently at very slightly different times in different bits of the space-time. And so you get bits that stretch out a bit more and bits that stretch a bit less, because the end of inflation is not instant. It's not literally the same time. And so that's the explanation for the ripples in the density of particles in our universe, which ultimately led to the formation of the galaxies. So, without those ripples, we wouldn't be here, is a standard thing that's said, and it's true. Yeah. But they seem to come from quantum mechanical fluctuations in the universe, when our patch of the universe was very small, much smaller than an atom.
It always does my head in when like the picture of the cosmic microwave background is somehow a picture of something that's smaller than an atom.
Or was. I mean, by the time it was that big, the universe, our universe, was 1,100 times less smaller than it is today.
Right.
Because the redshift is 1,000, about 1,100.
Right. Okay.
So yeah, so it was just over 1,000 times smaller in volume.
And is that the observable universe, presumably? Yeah. I've got one question, Jamie, that I need to ask, which is there's we've got on the podcast the Space 2020 awards. I won't bore you with some of the categories, but I want your nomination for the best bit of science this year. I'll give you the nominations. I want your opinion, which one you think is the best. First one is phosphine in Venus's clouds. Finding an FRB in our own galaxy and sort of relating it to magnetar. Finally observing the C and O cycle in the sun. Hayabusa's sample return. Or Virgo and LIGO spotting a black hole merger in the mass gap. Which of those is your favourite science story? Or is there a better one for the year? It sounds like your holographic one is better, to be honest. If only I'd known.
Yeah, but it's related to black hole research. I've got most excited by black hole research in general, both the observations of the collisions and mergers. And the last time actually I saw Stephen Hawking give a talk. It was one of his birthdays in Cambridge, and he said it was just after the first observation of the mergers of black holes, pretty much confirming his area theorems, by the way, which are part of the fundamental work that he did. And he said that he was excited because we're now into the observation, the observational phase of trying to understand black holes for the first time. So that is, I think, really profound. I'd add one though, is the vaccine.
Yeah, I mean, yeah. I was trying to keep it space related, but yeah, I mean the vaccine clearly. Yeah, that's clearly the most amazing.
It's an astonishing story.
Yeah.
But so yeah, I'd probably just go because I'm biased because I'm interested in black holes at the moment. So I go, the phosphine in the atmosphere of Venus, I think it's still disputed now, isn't it? Yeah. It's a very difficult measurement.
Yeah.
So we're not really sure about that.
Yeah. Yeah, the black hole mergers is just insane. I just can't believe you can see the ripples in space-time. Neither could Einstein. He didn't think it was going to be possible, did he?
No, and I mean, I remember visiting LIGO in when was it? 2008, I think. And even then, people were really skeptical about this thing. Going, really? We don't think you can do this.
Yeah,
and that's why Kip Thorne got the Nobel Prize. Yeah. I mean, he drove that against tremendous opposition. People just thought it was an impossible measurement. And then I think that we're surprised, everyone's surprised, the number of them. I mean, then you get into a whole other thing, which is where are all these 30 solar mass black holes coming from?
Yeah.
Which is telling you something about the early universe. It's telling you something about the first stars, presumably. So that becomes interesting. And then you start thinking, well, so it's another thing for the future is we're not really sure about the formation of the first stars in the universe. This tells you something, I think, about that. But the square kilometre array that's been built now, Jodrell Bank has just been named, I think it was today actually, the headquarters. It's always been the headquarters for the development of SKA, which is a big radio telescope array in Australia primarily, and also I think hopefully South Africa. And that's going to be able to look at the formation of the first stars for pretty much the first time.
Yeah, I had
in detail. Anyway.
I had Emma Chapman on a few weeks ago, and I read her book because and that's amazing. The first stars, that sort of early light of the universe. What an incredible time to be alive if you're studying that.
It's wonderful because you don't actually see the stars in radio. You see them punching a hole in the radio emission, in the hydrogen emission line. So you see the holes punched in the universe, as it were, or in the noise. Let's say the radio noise by the stars.
Yeah, that's ridiculous. And talking of stars, Brian, I was reading about Breakthrough Starshot, and if we could send one today and see the results, what would surprise you the most? If we went to Alpha Centauri,
I think the interesting thing is not the star actually; it's the exoplanets. So it's the system. We want to go to another solar system. We know that most stars have them now, but we really don't. We know something about the exoplanets. But as we know in our solar system, it's like, we observed our solar system much more closely than we've observed any exoplanet system. And we didn't really know anything about the places till we went there. To be honest.
No, I know.
We still thought there could be.
Yeah.
In the 1950s, you could have argued Patrick Moore. I remember Patrick Moore arguing in the 50s about life on Venus, until we started pointing radio telescopes at them, really, and seeing the temperature. Mars, very surprising when Mariner 4, went past in the 60s, the early 60s, and saw a surface that didn't have vegetation or canals. Even we had to go.
Well, it's like Pluto as well, isn't it? I mean, Pluto. Who would have thought it looked like that? I mean, and that's only a few years ago, and that's with Hubble and everything else. Yeah. It's crazy. Jamie, should we ask our usual 2 questions at the end?
Yeah, go on then.
First question is a science hero or a hero of yours that you would bring back from the past to show them what's around today, to try and blow their mind. Who would it be?
There are there's obviously so many really obvious answers. I'm trying to think of a not obvious answer. I think not obvious, right, would be give us another year or so, and I'd love Stephen Hawking to be able to see what's happened. Particularly with this solution to the problem that he posed back in the 1970s. We're not quite there yet, so I'd wait a year or 2, and then I'd show Stephen what's happened.
I'm getting very excited about your book now. Hurry up and write it. Sort it out.
We're hurrying up. It's got to be. Look, I'll be in court if it's not out next week.
Right. Okay. Brilliant.
There we go. We've got a date.
Wow, that's great. Nothing better than the threat of jail.
So, and Brian, I did mention that we have a space playlist on our Spotify channel. What would be your space song?
Well, I would go for off-piste Sibelius, 5th Symphony, 3rd movement. And when you hear it, especially if, like me, I wasn't really particularly knowledgeable about classical music or anything. I've grown up listening to electronic music and so on, and making that music. And but recently, just listening to particularly that period, for me, the 1910 to 1920, maybe a bit before, these people, Sibelius, Mahler, they just harmonically, you'll recognize it. But when you listen to it, if you know anything about science fiction or watch science fiction films, you'll hear every science fiction theme in that music. I mean, very vividly Interstellar. I think Hans Zimmer did say that Sibelius was one of his inspirations for the theme of Interstellar. It's not a science. Obviously, it's written in the 1914, 15, 16, that period in Finland. It's a hymn to nature. It's nominally about swans taking off a lake, but it's also undoubtedly about the beauty and power and mystery of nature itself. But you hear everybody's taken, every composer that's ever written anything for science fiction has listened to that, and it's in there. So it's one of the most cosmic pieces of music, I think, that I know. It's beautiful.
So colourful.
It's absolutely incredible. And for those of you who didn't watch Brian's show at the Barbican, are you still able to get a ticket for that stream on the Barbican site, do you know?
No, I think you're not. It was one of those things which was a one-off, and you had to listen to it. You had to book beforehand. It was a live performance. And so, no.
But isn't it going to be on the radio?
It'll be on the radio.
Yeah.
So, yes, on Radio 3. And you'll be able to hear that. Yeah, that's true. On BBC Sound, you'll be able to listen to the concert and what I said. But visually, no. Visually, the next time you'll be able to see that is on my tour, which is... so I'm touring October next year, end of September and October next year in arenas. And the Sibelius will be there. And this O'Neill cylinder behind me, fully realised by a great artist called Eric Vernquist, who's in Stockholm. He's done loads of work on it. So you can come and see 35-metre wide LED screens with a massive sound system and my version of 2001. which is essentially what I've done. So, and then the hope is sometime in 22, probably the end of 22, to bring it back with an orchestra. So our hope is that we'll be able to put the show, a different version of the show, into Royal Albert Hall, maybe Bridgewater Hall in Manchester with a live orchestra.
I really hope so, because it was just so perfect. I can't endorse it enough. And you mentioned electronic music. I wouldn't be doing my job. I need to keep my employers happy by mentioning Roland. I know that you obviously used to play synthesizers in a band and still play. Can you tell us a bit about your history with Roland?
My Roland history, I was always Roland, actually. So when I started, I joined a band called Dare when I was 18, which was a band formed by Darren Wharton, who used to be the keyboard player in Thin Lizzy. And so he came with this legacy of great synths. We used to use an OB8. That we were very lucky if it lasted an hour on stage, the OB8. And it had a MIDI retrofit as well. And it was just, all over the place. So we moved very quickly. I had the first Roland I had was a JX8P, actually, which I bought with the advance that we got when we signed a deal with A&M. So I did a JX8P, and then shortly after a JX10. And then the S50, which I used extensively, actually. And I loved the S50 because it was good for live performance, because everyone had S900s as well at the time, the Akai. But the S50 had the monitor. And because you're loading floppy disks on stage, right, between songs, you really want to know if that's worked. So I had 2 boxes of them back over. And just the fact that you could have a monitor sat there so you could see it really easily was really great, I think. So I loved the S50. And then we used a MC300 actually as the sequencer. So I used that on stage for many years, and always I think I don't think I ever did a gig without the JX10 and the MC300 with that band.
Amazing.
And I've still got the JX10.
Well, we know
it's in.
You've still got the JX10.
It works. Some of the keys don't work, but I think all the oscillators work. I think it's all behaving itself. So, but now I've got the Phantom to plug into it. So I'll play it off the Phantom, because the Phantom is, the JX10 actually, one of the most reliable synths I've ever had. It never let us down on stage. And the S50 didn't really. Very rarely missed a load of a disc. So unlike the OB8, the OB8 was an absolute nightmare.
That sounds terrifying, changing floppy disks on stage. What kind of sounds were your favourites in those early days?
We used a combination. We also had a DX7, I'm sorry to say. So we used the DX7 used to do the really twin. I had a D50 eventually, which we used quite a lot as well. But we tended to use like a sort of a real harshy kind of rock piano on the DX7 with a bed on the JX10. Lead lines. There's a song called "Into the Fire" on the first Dare album, Out of the Silence, which is the JX10 brass kind of lead. So I used to use that a lot. Nice. And we used to use the S50. We used it for some backing vocal samples. So we kind of in the late 80s we were. In some of the songs, we had these huge bits of backing vocals, and so and occasionally when we wanted that, the drummer would have a click, and we'd trigger backing vocal samples, it is terrifying. Because the one thing is, for me, because I'm on stage, and if I load the wrong disc, if you've got a backing vocal sample, the wrong backing vocal sample comes in.
Oh my god!
So you see the wrong song, and then your secret is blown. Then.
Yeah. We've both seen our fair share of on stage, because we both worked in the music industry for years, and being a tour manager, the amount of times I've seen stuff on the side of the stage that just your heart drops, because people look around and it's like, who's going to do something
I've actually been in that situation of loading up the Pope's vocals. Remember that gig at Westminster Cathedral, Jamie? Oh yeah. I had to load the Pope's vocals onto a sampler, and it was like exactly the same situation. Floppy disk. Had to hope that it's the right one, and the bloke in the orchestra is playing each of the things. It's like, please be the right one. Please be the right one. It's like, oh my god.
I used to turn it down. So I went through a phase of having the S50, and I'd load the disc, and I'd always turn it down when I was loading the disc, and I look at the screen and make sure it said the right song name, and then I'd turn it up again, and I got into that habit, But I had like 7 or 8 keyboards on stage. It was ludicrous, like Rick Wakeman.
Are you still recording music? Is it just a hobby now, or are you actually like recording your own stuff still?
No, it's kind of a hobby. I mean, I tend to play piano more now, so I tend to sit there playing piano. But I've got started playing around again. I got the JX10 out of storage basically and started playing around. And now, as you know, I've got a Phantom to play with. So I'm going to start. So I probably will start.
Well, what's great about the Phantom is you've got the V-piano technology in the Phantom, so you can model any kind of piano you want.
Yeah,
I can't wait to hear what you get up to.
Yeah, no, I can't wait to start playing with it because it's quite a machine. You know, that's the thing. You know, I could have done these gigs that I did in the 80s with just that. And the height of it, the height of the madness, I had a JX10, a JX8P in front of me and a D50 on top. So I had three in front, JX10, JX8P, D50. And they had two DX7s on the side. The S50 sat there at the back. And I had an S900 as well, because we used that voice sound on the S900. You could never quite get it on the S50. And then two DMP7s, the Yamahas.
Jean-Michel Jarre would have been proud.
It was just literally that sort of crap. You know, it was just absolutely ridiculous. And then the MC300 as well on a little thing there, because I had two discs, right? MC300 and S50 all over, and the S900.
So three. It must have been so stressful, because I sort of think about modern bands, young bands that I work with that we endorse, going out and their stage fright and just trying to, you know, just get everything nailed, do a good show. But the idea of, you know, that time when not only did you want to entertain people and nail your parts, but all of that technology that could and did go wrong, that's terrifying.
Well, yeah, and my first professional gig, by the way, was supporting Jimmy Page. So talk about stress.
No pressure.
Like, don't want to mess this up. And then Gary Moore, and then Europe. We supported Europe for ages, like 60 odd gigs, I think, over 3.5 months. More, so they were quite big gigs in the end for 3 boxes of floppy disks. You know, something always went wrong.
Did you ever notice Jimmy watching you from the side of stage just for some added
every gig,
nerves?
Every single gig. That's what's amazing about him. What for a young band? We're just starting out. Yeah. And he watched every night.
Amazing.
Yeah, incredible.
One last thing we were going to ask you to do, you can totally say no, is we were wondering if you could just do a little welcome to the Interplanetary you're listening to the Interplanetary podcast.
Well, I can't do as well as Brian Blessed. I remember on the Infinite Monkey, he was on the Infinite Monkey Cage once, and he just said, Robin Ince, my co-host, said it's like going on holiday on a dormant volcano. Having Brian Blessed.
Yeah, it was so insane.
Matt, I mentioned to Brian the interview where it was the interview we did with him. We did it inside the BIS, and it was maybe 3.5 or 4 hour interview where his manager would just kept sort of looking at us and was like, you know, like stop. But he wanted to just carry on. He's telling us these stories about, like the Bermuda Triangle and punching polar bears in the face. And me and Matt were like, this is incredible. Like, I don't want it to end.
You can't repeat most of it. It's unbroadcastable.
Yeah.
Yeah. I remember he was sat there. Well, I'm not going to do the unbroadcastable ones, but he was sat there and we were talking about Mars, I think. And he just went, Brian! To me, and I was like, "What?" And he went, "Why can't I fly through the middle of Jupiter? It's a gas planet." I'm just like, don't know. Oh, wow. There's nothing to do with what we're talking about. You can't.
Incredible.
You know. Anyway, I can.
The Interplanetary podcast is alive.
There we go. There was our Brian Cox interview.
There we go. I hope you enjoyed it. Yeah.
No, I love this guy. He's at the top there with those that we were always wondering who is the next Carl Sagan, right? Neil deGrasse Tyson, Brian Cox. Who else is there at the top of the best science communicators?
It's those two and us, isn't it?
Pretty much.
And us four. Yeah.
So,
that's it.
What are you guys doing this week for Christmas?
Oh, well, I'm experiencing something akin to Escape from New York. I'm basically Snake right now, trying to make sure that we get out of Norway before everything closes. Like Germany, Belgium, and Netherlands have all stopped flights out of from the UK and probably to the UK. And Norway is considering it. We've just moved our flight to tomorrow instead of the day after, and hopefully I'll be home with my mum by Christmas Day. So keep your fingers crossed for me, Spodcats.
Oh,
we will.
Or make that Sainsbury's advert extra poignant.
It will.
Julio, what about yourself?
Well, as Chris mentioned, when the Netherlands went into hard lockdown, which I have to say is quite more relaxed than the French hard lockdown. In France, you had to stay at home. Here, people can be outside. We just canceled everything. I was planning to have my sisters over. They live in Germany, but it's just so many risks that are not worth it for an artificial date that we choose, that we call Christmas.
Yeah.
We can meet later once this is over.
Jamie, what about you? And by the way, Jamie, I chose the quote at the beginning of the show, especially for you. I thought, it tied
Don't
in,
make me cry
tied
again.
in with the winter solstice. But it's good to have
It's
good to have you on.
It's great to be back for this special one, and we'll have to do it again in the future because I just love talking about stuff I don't understand. So that's why Brian Cox was the perfect person. Talking about. I mean, I told you, and this is true. I couldn't sleep for days before because I kept thinking about Big Bang questions to ask him. I thought I'm never going to have another chance, and so he absolutely indulged us. So. Yeah, it's been fantastic. So yeah, I'm going home. Well, I am near home for Christmas, and hopefully see a few family at distance on Christmas Day, and that's me. I just spent a near fortune in Waitrose, and I think I'm looking to consume at least 95% of that, including Matt. Have you ever had those Biscoff ice creams?
Oh no!
Biscoff, the biscuits.
Yeah.
They do an ice cream, and it is. I mean, it's to die for. It's
No,
ridiculous.
nice. Oh, I might.
So there we go.
See if I can
I'm still looking to get. Still getting to look to get some free food from this podcast. So if you're listening,
yeah, that's a good.
Get in touch. We'll give you our address.
I'll go out and buy some, and that'll be my Christmas pudding.
There we go. Done.
But yeah,
what about yourself, Matthew?
Oh, I'm just gonna stay at home, hunker down. Like Julio said, look, it's just one day. It's just one day, and we'll get through it. Next year's going to be absolutely awesome when all this is kind of, blown over a little bit. And I just want all the Spodcats to stay safe. That's why this episode is so long. It's to keep them keep them in the house longer.
Matt, why was January 1st? Why do we choose New Year's when we choose New Year's? Is there you're the closest I have here to an astronomer? Why is it not any other? Why is it not matching one of the solstices, for instance?
Yeah, I can't help feeling that it's drifted from the solstices. Surely, all these things are a kind of fudge, aren't they? Over the years to try and make the calendar fit. The calendars are a mess, aren't they? They're a total mess.
The big question for me is why did they choose the Brexit deadline for the 1st of January?
Oh, God.
Had to be sometime.
What a come down. Unreal.
Maybe because people are not reading the news that day.
Yeah.
Very
who
true.
knows?
Very true.
Well,
But hey, next year, maybe the four of us can get together,
I'd love that.
share some food.
Well,
I'd love to give you all just hugs that go on longer than they should.
Yeah, I reckon
that would be nice.
Episode 250, we should all fly over to Holland and stop at Julio's place and do a podcast.
Yeah.
Do a podcast.
First of all, I'd love that. We can go cycling as well. It's very nice here. But we said we would do Paris. I think we owe it to Paris. At some point to go there and do a show there.
We should definitely do Issa Paris.
Yeah, but you can't get those marijuana stuffed turkeys in Paris.
But you can get heroin.
You can't have a smoke and a pancake.
We're just kidding, of course. We're just kidding. All right. Well, I think that's it.
That's it. You and your space cakes.
I better go and cook a roast dinner.
Yep.
Lovely to see you guys.
Lovely to see you all.
Yeah,
it's great to have you all
we'll
together.
see you soon.
A chaotic podcast. I dragged everyone in at the last minute. They didn't even know they were doing it. Awesome. Bye, Spodcats.
Goodbye.
Bye.